My name is Seyyed Ali, and this is a joint work with Hyun Park, Professor Marcus Botacin from Texas A&M University, and Yichen from University of Toronto. This is the plan for the next 20 minutes, hopefully. So in the meanwhile, I want to mention that I know what some of you might be thinking, that like acoustic attacks, really? Like I thought we solved this problem like years ago. So I'm here today to say that why ASCAs still matter. In fact, they still matter more than ever. And we talk about our pipeline and our methodology for mitigating noise in acoustic attacks. So I want to ask with this question, do you think that this is a good password? I mean, sure, if you are a robot, but if you are a human, you have to type it down, write it somewhere, save it in an application. So we switched to something better, passphrases. Is this a good password? Well, that's interesting to know that this is almost equally secure as the previous password. That's what mathematics says. It has the same entropy. So we have started using passphrases, and they become the best practices for human typing passwords. We use them every day. So they are strong, they are memorable, perfect. But are they truly secure in any environment? Unfortunately, if someone listens, records you, or maybe on a Zoom call, they can just easily record the Zoom call. And when you are typing your passphrases, they can record the audio of the keystrokes. So the attacker setup is very simple. All they need is a microphone or a recording. So a question appears, so if this is like this simple, why we aren't getting hacked this way every day? The solution is one word, noise. Noise is everywhere. You might be in a coffee shop. You might have a dog barking in the background. And noise is the biggest challenge for acoustic side-channel attacks. Here is an example that clarifies this matter. So figure 5A shows a clean spectrogram of a clean audio, like an audio that recorded perfectly with noise cancellation. And we can see the distinctive patterns in this spectrogram. But if we just add a light noise, like just a little bit, 10%, all the distinctive patterns disappear. And it becomes very difficult for the model. And the model starts random guessing. The impact is huge. The state-of-the-art model, which the name is CoAtNet, on the clean data set can achieve an amazing 99% accuracy. But if you add this light noise, the accuracy drops significantly. So the first question that we ask is, what if we change the model? What if we use another structure of vision models and use vision transformers? And even if those fails in noisy condition, then what is the solution? Well, we came up with this pipeline. We actually split the problems into two problems. First, we classify the audio spectrograms with vision models. And then we treat the results as a sentence including typos, a sentence with typos. And then we prompt the LLM to fix the typos. So the question is why this works actually, like why this will work. It's very simple because passphrases are patterns. They are not random strings, they are not random characters, they have patterns. And guess what? LLMs are the best in detecting patterns and fixing the typos. So here is an end-to-end example. So the reference is a sentence that is the correct ideal that we expect to have as an output, and it's what the user types on the keyboard. As we can see, the CoAtNet output is not readable at all. And the LLM can fix this typo to a very good extent. Just it couldn't guess the strong word, but it used the word tough, which I would say is acceptable because it has the same meaning. So let's dive into our pipeline. The first stage is the vision model. For the pre-processing, we use time shifting, time and frequency masking for data augmentation, and then we transform it into a 64 by 64 mel spectrogram, which is a standard in vision models. We also tested with 128 by 128 spectrogram, and the results are very same, just the numbers are shifted a little bit, but the overall ranking is the same. For the vision models, we fine-tune the state-of-the-art CoAtNet model, and we also compared the results with 5 different vision transformers. And all the experiments are done on 2 public data sets. One is recorded on Zoom application, and one is recorded with the phone, with an iPhone directly. Both data sets contains 36 keys of the keyboard, and each keystroke is repeated 25 times. So here, as we can see, the fine-tuned CoAtNet model achieves the highest score, and now it's the state-of-the-art model in this application. And we can see something interesting, that some vision transformer, specifically swing and bait, they can achieve very comparable and close accuracy, close to our state-of-the-art model. And it indicates a message that if we have a large and good data set, vision transformer can outperform the CoAtNet model. For the next stage, we used the synthetic Gaussian noise in 3 different levels, low, medium, and high. And by low, I mean 10% accuracy drop. By medium, I mean 20%, and by high, 50%, respectively. We can observe that the model, when we increase the noise level, the model makes mistakes due to the noise, and the output contains typos, and in some cases, the output is even unreadable. So can an LLM fix this? So when we are using the LLM, the prompt that we give the LLM matters. So we use a few-shot technique. So we gave the LLM some sentences, 2 sentences, and the corrected sentence, and with the hope that LLM can learn the noise patterns and fix the new sentence. For the evaluation, we use 5 different metrics: BLEU for precision, amateur for recall, and ROG for overall structure of the sentence. And here is the results of the LLM stage. So as you can see, the blue one is the baseline, the CoAtNet model. And as you can see, the accuracy drops significantly under the noise. But the LLMs that we use, Llama 1B, 3B, 8B, and GPT-4o, So at that time that I was doing the experiment, GPT-5 wasn't released. It released recently, so we don't have the numbers for that. But we can see that the LLM is doing a great job. It's increasing the accuracy, and we can be hopeful. But there's one problem. The problem is we cannot use GPT-4o offline yet. And even if someday OpenAI release the weights of GPT-4o, it will be very big, very resource intensive. Even if you decide to use the other open source models like Llama 8b, they are still resource intensive. You need at least 16 gigabyte of VRAM to load this model. And it's not practical for low resource or stealthy attacks. And it's very expensive to deploy at the scale. So our goal is to have a small model that you can fit and load on your laptop and use that in this scenario. So we picked Llama 3B model. I can actually load it on this laptop, and it's suitable for practical and real-world attacks. So we fine-tuned this model, and the results are very good. In all the noise levels, low, medium, and high, it can achieve 90% the performance of GPT-4o with 1.5% of its size. Well, not only this work, but the field of acoustic side-channel attacks has some gaps, including the dataset availability. Unfortunately, the public available datasets are small and tiny, and they don't have the they don't include all the keys like space, backspace, caps lock, tab, and also they are recorded in perfect settings, noise the best mics, but in the real world we have ambient noise. And also they are limited to only one device, one keyboard. So if we have like a cross-device dataset, that would be great. So if you are working in side-channel attacks, our call to the community is to create large and open access datasets with real-world ambient noise on multiple devices. To conclude this work, I talked about vision transformers. They achieved accuracy very close to the current state of the art, and they are showing a strong potential for keystroke spectrogram recognition. And LLMs are essentials in this pipeline for the post-processing. And also fine-tuning, with fine-tuning, we can make this attack practical and portable. The security implication is that the passwords are gone, passphrases are in danger, and we should adapt multi-factor authentication, biometrics, hardware keys to mitigate this attack. All of the experiments and source code are publicly available at GitHub. It's functional, and the results are reproduced. So check it out. Yeah, the slides will be uploaded very soon. Thank you.